Hello guys, so today we will learn linear regression and least mean square as statistical learning and gradient based optimization. So let us start with supervised learning formulation. So as we are given with the data set with a training set of m examples, like x are the features and y is the target, and there are m instances or m samples, and our goal is learn a function from x to y such that h of x is a good predictor for the corresponding value of y. It means that h is some function, and when we put the value of x, we get y. So we want that hx is a good predictor. When the target value y is continuous, we call the learning problem a regression problem. So when the y value is continuous, like house price or a diamond price or weight, these are continuous values. So this type of problem is known as regression problem. And when the values are categorical, these types of problems are known as classification problem, which we will study in our next lecture. So, firstly, we will learn about hypothesis representation. So, hypothesis or model. So, firstly, we will know what it means. To perform linear regression, we decide to represent h as a linear function of x. So, here h, that good predictor which we are talking here, that only. So, h theta x is equal to theta naught plus theta 1 x1 plus theta 2 x2. So, this theta 1 and theta 2 and theta naught are weight value, or you can say theta naught as bias also, and theta 1 and theta 2 as weight, and x1 and x2 are the features. The bias trick. To simplify notation, we define x naught equals to 1 as the intercept term. So to simplify the notation and to make all the notation in terms of weight, what we think what we think as x naught equals to 1. So x naught equals to 1, then this theta naught also becomes some weight. Theta naught also belong to the weight, so that we can represent in the form of matrix or vector. So vector notation, the hypothesis become a simple inner product. Now you can directly write it as theta jxj summation 0 to n. So which is like theta t is generalized form, we can write as theta transpose x. So here theta is weight and x is that all features, x1, x2, x3, all. So the objective function. So what is the objective function? That is also, we also call it as cost function. We define cost as j theta, which measured how close h theta xi to the corresponding yi. So h theta xi, what it is? It will give you uh, that predicted y value, and j theta tells us how close is predicted to the actual y value. So we find objective function as h theta xi minus yi whole square, and we put 1 by 2. Now we will there is actually a intuition behind putting 1 by 2. Whenever we will differentiate it, this 2 will come here and they will get cancelled. So that's why we are putting it like this, and that's why it is square also, because we don't want that gradient become very complex after differentiating. That's why we put a square. So the squared cost error for linear regression is a convex quadratic function ensuring a single global minima. Yeah. So here you can see, start with some initial theta. We will take an initial theta or weight value as random, or there are many different initialization technique. We will learn it further in the course, and repeatedly perform the update. We will update it after every iterations. We will update our weight and we will find a new weight. So the updation rule is like this: theta is equal to theta j minus alpha. Alpha is the learning rate and gradient of loss function or objective function. So update occur in direction of steepest decrease and negative gradient. This is performed for all, so we have to perform it for all weights like 0, 1, 2. So here, like in this equation, there are three weights: theta 0, theta 1, theta 2. So we will perform it for all weight, and this you can see the objective functions graph, how this loss decreases. It's decrease from here to here. This is the minima. So it depends on alpha value how fast the convergence will happen. So if it will be very high, that is also a problematic case. When it will be very high, it may happen that it overshoot the minima, and if it is very slow, then it will take a very long training time, long computational timing. Okay. So now we will find the derivative of cost function. So here for a single training example, let take x comma y. Let's compute the partial derivatives. So we will compute the derivative of j theta with respect to theta j. So after here when we will differentiate it, this 2 will come out and this will get cancelled, and after differentiating differentiation, the value will be uh, we will apply we will put the value of h theta xi, and the value is theta xi, and after differentiating it with respect to theta, we get value as xj, we get value as xj. And now the combining the derivative for single training example, the update rule is like theta j equals to theta j plus alpha yi and minus h theta xi into xj xi. So what happening here? So when we differentiate this value, yeah, we will put it here. So after differentiating, what we are getting? So after differentiating, the value is h theta xy, and here after differentiating this part, we are getting xj. So we are putting xj here, and we are putting xj here, and when we are multiplying minus alpha to y minus y, it is becoming plus alpha y, and the remaining part h theta x, when we get multiplied. So uh, yeah, so it is yeah. Yes, so this alpha is actually in on this whole term. This is like together, and alpha is outside it. So this is Widow-Hoff learning rule. And now vectorized design matrix. So define the design matrix X and vector Y. So X, what is X? X is that vector feature matrix. So feature matrix, there will be like there are m samples. So there will be m samples and n plus 1. Why n plus 1? Because there are n feature and plus 1 for the extra term which we had taken here. This theta naught, for theta naught we are assuming that our one feature is like one extra feature is have value 1, x not equals to 1. So that's why here m into n plus 1, m into n plus 1. Each row is a training example feature. Yes, each row is a training examples. And now the cost function will be here in terms of matrix. If matrix is theta x, and y is the actual value. So as we have seen there, 1 by 2 x 1 by 2, this one whole square. So in matrix we don't write a square, we can write it as like x theta minus y transpose into x theta minus y. So this is your cost function. Now we will differentiate it in terms of theta. First we will expand it. After expanding, we get it as this, and then we can note it like this value, and this value is a scalar. This value and this both are scalar, so this will combine and will be 2 theta transpose x transpose y. Now now we will multiply 1 by 2 inside, and after multiplying it and differentiating it with respect to theta, we get it x transpose x theta minus x transpose y, which now and after differentiating it with respect to theta and setting it 0. Why we are putting it 0? Because we want that our cost function should become our cost should become 0. I means our loss should become 0. So we are putting 0 here because we want to minimize our loss. So when we will equate the differentiation with equals to 0, we'll get the exact theta value which will minimize this value, which through which we will get the minima of this value, this cost function's value. We will get minima. So after differentiating this value, after differentiating and after putting it 0, we got theta as here for getting theta we can multiply it by x transpose x inverse at both side, then we'll get theta as this value. So when we will put this value inside this, we will get the minimum cost function value, or the minimum cost. So we want to have a minimum cost. That's why we are doing this. Now geometry of least square. So the prediction y bar equals to x theta must lies in the subspace spanned by x. Yeah. So here is your actual y and this is your predicted y. We want that the error should be to minimize the error, we have to choose theta such that y bar is the orthogonal projection of y, because if it will be the orthogonal projection, the error will be the minimum. So that's why we want it as a orthogonal projection of y. So now the residual y minus x theta is the orthogonal projection, is the orthogonal to all x. Now this y minus x theta, this one, is orthogonal to all this x1, x2. So we can write it as x transpose y minus x theta, and this is actually error. Y minus x theta is error. So x transpose error into error equals to 0. This is orthogonal complement thing. So we know x transpose because the angle between them will be 90 degree. That's why this is x transpose dot E equals to 0. So yeah, it means that x1 transpose E is also equals to 0, x2 transpose E is also equals to 0. Now learning rate. So I have told you, like, when alpha value will be very slow, very small, then it will be slow convergence and it will take a longer time because it will be taking very small steps. And if it will be right value, then it will converge in a converge easily and will not take longer time and will not overshoot the minima also. And when you will take large value, it may happen like it will overshoot the minima, it will not converge to the minima. So now underfitting. So underfitting is model is too simple and fails to capture the trend. Here is the example. When balance fit, like, yeah, this curve you can see this is balanced one because all the points are near to this curve. And when model is overfitting, like you are trying to fit your curve properly, totally towards the data. So then what will happen? It will l- in spite of generalizing the data, it is actually learning the data. So when a very when in test there is a little different data will come, it will not be able to predict. So when model will become too complex, it means that high variance fits the noise instead of the signal. So that's the problem. That's why actually, when we make it too complex, then it also fits to the noise data, which is very far or outlier type of thing. So when a different type of samples come, it is not able to predict, because it is in spite of generalizing, it is learning the data, totally memorizing the data. That's not correct thing. So yeah, so we have covered linear regression hypothesis, MSE cost function, optimization through LMS and gradient descent, and analytical normal equation. So if you have any question, you can ask in comment. These are the image sources. Thank you.